Alrighty, we are going to do some Chapter 7 review, and then you will move on to reading and taking notes on Chapter 8.1, which I will begin going over tomorrow. Don't forget that your Chapter 7 quiz is on Friday, April 2nd, so next Friday. Alright, so magnetism. Magnetism is the property and interactions of magnets. It is a basic force of nature, just like gravity and electricity, and it's the tendency of certain objects to pull or repel other objects. Okay. A magnet has it produces what's called a magnetic field. And a magnetic field is this region of space that's around a magnet, and it exerts a force on other magnets or magnetic objects that might come into contact with that field or into that field's area. And a magnetic field and the magnetic force, they're related. The stronger a magnetic field means that the more force that a magnet places on any objects that might be in that magnetic field. So stronger magnets have stronger magnetic fields, so they produce more magnetic force. This is kind of similar. A big idea associated with a magnetic field is proximity. Proximity means closeness. So if we have a magnet with a magnetic field like this, as we get farther away from the magnet, we feel less force from the magnet, right? If I hold another magnet right here, right here, right close to this magnet, if I hold another magnet right here, that magnet or piece of magnetic material, that material, whatever it is going to feel the force, if it's magnetic also, it's going to feel the force of the magnet's magnetic field. But if I hold a magnet really super far away from this magnet, it's not going to feel the force. So the further away we get from the actual magnet, the less force the magnetic field lines have. And this is kind of similar. It's kind of a weird concept, but if you want to think of it as, if we have the Earth here, this is the Earth, and here I am standing on the surface of the Earth. I don't fly off the surface of the Earth, right? I don't fly off the surface of the Earth because the Earth has a gravitational field, meaning that the closer we are to the Earth, the more gravity that we feel. It's exactly the same as magnetic fields, but it's a gravitational field. So this gravity, as we get further away, for example, if we get so far away that we're at the moon now, the moon still feels the gravity of the Earth, but not as strongly. If I was standing on the moon, I would not feel the gravity of the Earth as much because I'm way far away from it now, right? So the further away I get from the object, from the Earth in this case, or from the magnet in this other case, the less I feel the magnetic field or the gravitational field. Okay, so now we need to look at what makes an object magnetic. What makes an object magnetic. But also real quick, you'll notice that the direction that the magnetic field lines are going are toward the south, right? So from north to south. Just so you know, just forgot to point that out. Okay, so what makes an object magnetic? We're going to have to look at these concepts of magnetic poles. We need to understand what a magnetic pole is, or just a pole in general. It doesn't even have to be magnetic, but just a pole. We need to look at this concept of magnetic domains. And that's it. Those are the two things we're going to look at in order to explain what makes different objects magnetic. So first, what is a pole? A pole, a magnet has two poles. It has a north pole and a south pole. So this just means opposites, basically. If we have a battery also has two poles. A battery has a positive pole and a negative pole, right? So pole just means you can think of it as just meaning kind of opposite, two opposite ends. Poles are opposite ends. So the magnetic poles are the North Pole and the South Pole. And if it's a true magnet, you can break a true magnet in half. So if we have this magnet, this is the south and this is the north. If I were to cut this magnet in half, just like that, I would not have a north and a south. Now I would have two littler magnets. I'm going to draw this actually this way. I would now have two smaller magnets. Both would have a north and both would have a south. And then if I wanted to cut those magnets in half, I would have 4 little magnets. They would all have south poles and they would all have north poles. And I could do this over and 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 over again until I got down to what's called the subatomic particles, or the atoms that make up the magnet. Remember, an atom is it's a tiny little building block of matter. So we need to understand this. We've talked about this before, I think. Atoms are the kind of the cells of matter. So they are the individual components that make up matter. And atoms are made up of what are called subatomic particles. And I'm sure you've heard of the subatomic particles before. They are protons, neutrons, and electrons. All right? Okay, so we have this I need to explain these concepts to you. I needed to explain these to you and make sure you understand them in order for us to really understand what magnetic domains are. So we understand what poles are. We understand atoms and subatomic particles, I hope. So now we can talk about magnetic domains. Okay, so let's think about a material that is magnetic, like iron. We're going to talk about iron in this example. So we have some iron. All right, here's my iron. Okay, this is a block of iron. It's a big rock made of iron. Okay, in this block of iron, if I broke it down to its tiniest little particles, I would get down to its atoms, right? And its atoms would look like this. You've probably seen something like this before, okay? So if I were to zoom way, 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 way into this one piece of this iron, I would see atoms. And atoms, like I just told you, atoms contain protons, neutrons, and electrons. So the protons and neutrons are here in the center of all these atoms, okay? And spinning all around these blue lines, these little blue dots and blue lines, these are the electrons. And electrons have magnetic properties. They are charged particles, and they're basically little magnets. All right? So they look something, if we were going to think about them as little magnets, they're spinning all around, and they look something like this. So each little electron is its own little magnet, and the blue arrow means they're literally spinning around in three-dimensional space around this ball of protons and neutrons in the center. So imagine this is like a basketball or a football, and the electron is spinning around the center, all around the outside of the soccer ball, spinning around this center, okay? So each one of these electrons is actually a little magnet. It has magnetic properties. Each electron has a north pole and a south pole. In non-magnetic substances, matter, in non-magnetic materials, the way that these electrons the magnets are, the magnetic properties of these electrons, they kind of cancel out. So what I mean by that is if we have all these electrons and they're all their own individual magnets, we have the north pole of this magnet facing that way, the north pole facing this way, this north pole facing that way, all pointing in different directions. So all of these different directions of the north poles cancel out, and that makes the overall atom not magnetic. Not magnetic. If all of the atoms are not magnetic like this, that means that the matter that these atoms are making up is also not magnetic. But in our situation with iron, what can happen is these electrons can kind of line up or spin in a way that makes all of their north poles and south poles face the same direction. So all the north poles are facing down, all the south poles are facing up, for example. It's not as easy as up and down, but so what that does is it makes the overall atom magnetic. It gives the overall atom it makes this atom into a magnetic domain, is the way you can think about it. So all of the atoms of a magnetic material, they're all individual magnetic domains, and they all end up facing the same direction, so that all of their north poles are pointing in the same direction, all their south poles are pointing in the same direction. So the magnetic domain is the individual atom, like in this case, or in this case, see here, we have all of these individual magnetic domains. This is one, this is one. Each atom is its own little magnetic domain. So in a magnetic material, all of these magnetic domains, they're all oriented in the same way. If they're all oriented in the same way, if all of the atoms are oriented in the same way, that means that our overall big piece of iron, all of the atoms inside are oriented like this, with north pole facing down. That means that all of the atoms inside this iron, all the north poles are facing down, so it gives kind of it makes the iron magnetic. It makes you could imagine it as the top half of the iron being south pole and the bottom half being the north pole. It's not necessarily exactly how it is, but it's an easier way of kind of thinking about it, okay? So these are all oriented in the same direction, making this larger piece of matter magnetic, all right? So that's what you need to know about magnetic domains. You need to be able to explain pretty much how I just explained that concept of how magnetic domains contribute to the overall magnetic properties of magnetic materials. And the main magnetic materials from your book that you need to know and that you should have read about are iron. Whoa, that is big. Okay. Iron, cobalt, and nickel. And that maybe seems random, but if we look at our periodic table here, we have iron. Oops, I don't want to write on that. Iron, cobalt, and nickel. They're all right by each other, and we're going to learn eventually that atoms that are or elements that are near each other on the periodic table share similar properties. So those are the three kind of the magnetic trifecta there. All right, so those three are the main magnetic materials, natural magnets that we are going to see and discuss, and that are discussed in your book and that you should know. All right, a permanent magnet is, that was something that some of you Oops, didn't mean to be... I meant to pause, but... Well, I just realized that I had been recording that whole time and pausing. I paused in the wrong spot when I meant to be talking. So, permanent magnets, sorry for the big, long, awkward silence, but hopefully you got to write all that down. A permanent magnet is a magnet whose atoms or magnetic domains are rigidly stuck in place with all the poles facing in the same direction, like I have here. So, iron, for example, permanent magnet, okay? A non-permanent magnet would be a situation where all the magnetic domains are not aligned in the same position. So we would have something, if we had atoms, for example, with, this is, let's say, the North Pole and the South Pole of that atom, the North Pole and the South Pole of this atom, the North Pole and the South Pole, the South Pole and the North Pole, etc., etc. So this is not a permanent magnet, right? This is not magnetic at all. All of those those magnetic domains cancel each other out. But they can still switch places. We could make this piece of matter into a magnet, but it wouldn't be a permanent magnet because atoms, these electrons are constantly spinning around. Like I said, they're constantly basically switching their poles. Their magnetic poles are not necessarily always in the same direction. But with permanent magnets, they are stuck in the same direction. Okay, so let's now move on to compasses and Earth's magnetic field real quick. First of all, what is a compass? Well, a compass is just a little magnet, right? A compass has a needle in it, and the needle is going to point north. All right, so in order to really understand how compasses work, we need to also look at the magnetic poles of the Earth. All right, so it's not just the magnetic poles we're going to talk about. We're going to talk about Earth's geographic poles versus Earth's magnetic poles. All right, so the geographic poles are north and south, like that. That's pretty simple. The Earth's magnetic poles are not the same. The Earth's magnetic poles are a little bit off-center, so they are not exactly perfect north as we imagine it, and they're not exactly perfect south as we imagine it. They're more diagonal like this on Earth's, not just straight up and down vertical. And the magnetic pole, the south magnetic pole, is near Earth's north geographic pole, and Earth's north magnetic pole is near Earth's south geographic pole. That is a lot to wrap your head around, but that is the way that it is. So south, this is I'm going to rearrange this. All right, there we go. We have the geographic north and the geographic south, and we have the magnetic south up here by geographic north, and we have the magnetic north down here by the geographic south. All right, so I just told you, let's look now at our compass over here. We have our compass, and we know that a compass points to the north, right? No matter where I'm standing, the compass is going to point north. So this was my very poorly drawn Africa right here. So if I'm over here in Mauritania, my compass is going to point to the north. Right? Okay, so if the compass is a magnet, the bar in the compass is a magnet. Okay, we're going to do a little brain thing stretch here. If the bar that I've drawn there, this is the bar, this piece right here in the middle that I'm talking about is the bar. This is the bar. This is a magnet, right? So that means it has a north pole and it has a south pole. Okay. All right, here's my compass. It's pointing north. where is the North Pole and South Pole on the magnet, on the compass? The North Pole of the magnet, always points towards the South Pole of the Earth. So that means that we have our north up here and our south down here, right? So no matter where I move it, that north is going to be pointing up here to the south geographic pole, right? It's south magnetic pole. Sorry, I misspoke. The south magnetic pole, right? Because the compass always points north. The north part of the magnet, the North Pole of the magnet, must point toward geographic north, which is the same as magnetic south, because the opposite ends of the magnets attract, right? Okay, so this is a question you're going to see again. Big hint. You need to be able to draw this situation, this right here, and explain to me what I just explained to you. So what pole of the compass is going to point to which magnetic pole of the Earth, which is the same as which geographic pole of the Earth, etc., etc. So you need to understand this concept. That's why I'm taking so much time on it. All right. Okay. There's another important thing about compasses that you need to understand. And let's look at how we could make a compass from everyday items. I think I wrote how we could, or I think it was interpreted. I don't know if I wrote it like that or if that's what you interpreted, but some of you said from the study guide, how can I make a magnet out of everyday objects? But we can't make necessarily that. I meant, how could we make a compass? If I wrote it wrong, that's what I meant. How do we make a compass out of everyday items?